Welcome viewers to the next session of the course Finite Element Methods for Beginner. In the previous session, we have discussed about the selection of polynomials for 1D, 2D and 3D problems depending on the degrees of freedom per node. And in this session, we will discuss how to evaluate shape functions at each node of 1D element. So let us begin our session. Let us assume that NFE be the total number of degrees of freedom per element, and it means NFE will be the total number of field variables. So this will also be equal to field variables per element. And if I assume that phi x be the field variable, then we will have phi 1e, phi 2e, dash 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 up to phi NFE will be the total number of nodal variables. And we know that the field variable can be represented in terms of shape function as n1x phi 1e plus n2x, or we can write this as phi x is equal to summation of I is equal to 1 to total number of degree of freedom per element, and ni x we are talking about one dimension problem, and phi I e. So this is how we can represent the field variables and shape functions. So now let us consider a 1D linear element. The value of field variable here can be represented as phi IE. Let us say this is ith node, this is jth node, and value of field variable is phi j e for this eth element, and xi and xj be the coordinates of this. Now we can write down that from our previous knowledge about the two noded element, we can have minimum two terms for representing our field variable. So phi I we can write down as C1 plus C2 xi, and phi j I can write down as C1 plus C2 x. So we can write this in matrix form as phi I, phi j is equal to the matrix we'll write later, and it is C1, C2. This is 2 into 1, this is 2 into 1, and this would be therefore 2 into 2, and this is also clear from this particular equation that it will be coefficient 1 of C1, and then it is C2, it is xi, and then it is 1 and Cj. Now our aim is to find C1 and C2 so that we can substitute the values here back into it to get the everything in terms of the shape function. So we will write as C1 and C2, that is equal to inverse of this 1 xi 1 xj all inverse, that is the inverse of this matrix. This will be equal to phi I and phi j. And inverse of this matrix we can write down directly, but let us first introduce what is the method of calculating inverse of any matrix. So if there is a matrix A and we want A inverse of that matrix, and inverse is only possible if determinant of A is not equal to 0. So we can write down this A inverse into A, that is equal to A inverse is equal to identity matrix. This is one of the property of the inverse matrix. And inverse is given by the formula for inverse is adjunct A divided by determinant of A. This we can find out using C transpose, and C transpose is nothing but the cofactor matrix, and cofactor matrix we can get, that is the element of cofactor matrix is given by, if it is Cij, that is the element of cofactor matrix, will be equal to minus 1 I plus j, and it is the measure of ij. So here I, it means if we are talking about 1 1, the first element, first row and first column, so it is 1 here. So these 1 1 plus 2, so it means it is positive of mij. So now we can write down the cofactor matrix for this particular matrix is C is equal to, this is xj. If I talk about this, so this is 1 and it is minus because it is 1 and 2, so it is minus 1. And if we calculate this, then it is xi, again it is minus because it is 2, I is 2 and j is 1, so it is minus xi, and then it is 1 similarly, and transpose of this would be the adjunct A. So it means inverse of this matrix. Now I can write down this formula or the expression, matrix expression C1 C2 is equal to inverse of this, that is given by xj minus xi minus 1 1, we are getting transpose of this, and divided by determinant of this matrix, and this is equal to xj minus xi. So this is what we get, and finally this vector field variable phi I and phi j. So this is what we have obtained, and we started from our basic equation of phi, that is equal to C1 plus C2x, and this now I can write as 1 and x in matrix form, and this is my constant vector, and this now I can replace this C1 C2 from here, so that I can get value in term it and the nodal variable. So when we substitute this C1 C2 from here, I am representing the field variable, the function of field variable in terms of the nodal variable as well as the coordinates. So what I will get 1 x, and in place of C1 C2 I write xj minus xi, and in matrix form it is xj minus xi minus 1 1 and phi I eth element and phi j eth element. If I multiply this together, 1 2 3 terms together, I get This is basically constant term. I can take it out. This is to be multiplied by this. So if I multiply this with x, it will be xj. This into this and this into this is minus x divided by xj minus xj minus xi, and then we can have this phi 1, or we will write it in the next step so that it is more clear. And this to be multiplied by this, I get minus xi plus x, because x is to be multiplied by 1 divided by xj minus xi, and this is to be multiplied with phi I and phi j. Now I can open this further to simplify the equation in algebraic form. I get this as xj minus x divided by xj minus xi multiplied by phi I e plus, now let us rearrange this, x minus xi divided by xj minus xi multiplied by phi je. So now I can write the other equation that we are using from the beginning, that is phi is equal to n1 phi 1 e plus n2 phi 2 e. Or for this I and j notation, we can write ni phi I e plus nj phi j e. If I compare this equation that we have just derived and this equation, this is the general form of the shape function and field variable, what I get is ni is equal to xj minus x divided by xj minus x, and nj is equal to x minus xi divided by xj minus x. And this is what basically was required. We have started our the analysis to get the values of shape functions. So these are the shape functions. Now let us discuss what are the shape property of what are the properties of this shape function. Then if we put x is equal to xi, if I take this x is equal to xi, it means I am talking about, and then I can find out what is the value of ni and what is the value of nj. It means when I substitute x is equal to xi, I am talking about ith node, and the value of the field variable of ith node from this, when x is equal to xi, so this is basically I. We get xi here, so xj minus xj minus xi, you will get 1, and when this is xi minus xi 0, so it is 0. So when when we are talking about node number 1, the shape function at node number 1 or ith node is 1, and the shape function for the jth node is 0, because we have the variation of this shape. These shape functions are dependent on x. They are dependent on x. So it means this will vary as x varies, and this will also varies as x varies. So if I draw this variation on this two-dimensional element, 1D element, two-noded 1D element, and this value, let us say, is 1. So this is the variation of shape function ni. When x is equal to xi, value of ni is 1, and when x is equal to xj, this value of ni will become this xj minus xj will be 0, and that is what you get here at this. And similarly, so this is the variation of ni, where, and the variation of nj would be opposite to this. At node number jth node, the shape function of jth node will be unity, and at all other node in general, though we are only talking about the two noded element, but in general, whenever we calculate values of shape functions at each node, the that node shape function is 1 and all other shape functions are 0. So that is what is the property of the shape function, and that property will be using a lot in our further analysis. And this next thing, at all other points, value of ni plus nj will be equal to 1. So this is another property of the shape function. So we have derived the shape functions on the basis of the polynomial that we have selected. So this is the one method. The other method of shape function derivation is the directly using some standard polynomials, and then we can directly write the shape functions rather than having this complicated derivation. So we have, it means now we have two methods of shape functions derivation. One is we have to derive after appropriately selecting the polynomial, and secondly, for directly writing down the shape function expressions on the basis of some standard polynomial. So that will be discussed later on. In the next session, we will just take up one example of 2D derivation or the shape function derivation for two-dimension problem. So that's all for this session. Thank you all the viewers for attending the session. Thanks a lot.